Assalamualaikum. This video is about my final year project entitled Modeling an LQR Controller Design for Kabupaten System. My name is Muhammad Amin Firdaus bin Cik Hashim from Faculty of Electrical Engineering. My supervisor's name is Madam Arfa Shahidah binti Muhammad Noor. These are the project outlines. First chapter is Introduction. The control of liquid level in tanks and flow control between tanks are fundamental requirements in process industries. These are some of the examples of liquid level system in process industries. This block diagram shows the representation of a typical liquid level system. These are the objectives of my project. The first one is develop mathematical modeling. Second one is design and optimal parameters of LQR controller. The last one is analyze system performance between LQR and PID controller. Next is the problem statement of the project. First one is liquid level in tank must be maintained in a specific contained level. Next is the PID controller seems to struggle to function well for Kabupaten system operations. And the last one is disturbance may arise during the process of Kabupaten system. This is the scope of the project. First one is experiments for verifications of the model and proposed controllers are conducted. Kabupaten liquid level system is modeled and simulated using MATLAB or Simulink software, and the system used is SISO, which is single input single output control system. Next chapter is literature review. This is the reference of the project. Next is the figure of Kabupaten system, and this is the configuration of Kabupaten system. There are two differences between MIMO and SISO, and there is one similarity between both of them. Next chapter is about PID controller, which is proportional integral derivative controller. The next is schematic diagram of PID controller. Next chapter is about the tuning method of PID controller, which is trial and error method. And this is the block diagram of PID controller using trial and error method. Next chapter is about the LQR controller, which is linear quadratic regulator. Linear quadratic regulator uses full state feedback, and this is the schematic diagram of LQR controller. Uses state space equations. Next chapter is about the methodology, and this is the flow chart of the project. The first is the research paper and literature review after the start. Next is determine mathematical model of Kabupaten system, and next step is design LQR controller and PID controller. After the confirmation of both systems are stable, we proceed with the last step, which is comparison and analyze the transient response. And this is the mathematical modeling, which has represented in PSM1 by using Trotsley's law Taylor series, and we can get the equation of the Capleton system. And next chapter is about the second order of single input single output for Capleton system. And after that we can get the transfer function of Capleton system. Next chapter is about the designing PID controller. These are some of the methods for tuning PID controller, which are trial and error method, auto tuning method, Cohen-Kuhn method, Ziegler-Nichols method. The tuning method is very important in control system because the values of parameters in controller can affect performance of the system. Next chapter is about the trial and error method for tuning PID controller, and this is the simplest method of tuning PID controller, and the steps are set integral and derivative terms to 0 first. Next step is increase proportional gain until output at a constant rate. Next step is set integral term once P response is fast enough. Next is to change I value until steady state error is reduced. And the last one is increase derivative gain until system react to set point. This is the design in MATLAB of trial and error method PID controller. Next chapter is about the automatic tuning method for tuning PID controller, and the step of the tuning is set the reset time to its maximum value. Next is set the rate to 0, and the last one is increase the gain until loop oscillates at constant amplitude. And this is the design in MATLAB by using automatic tuning method PID controller. Next chapter is about the conversion of transfer function to state space. This is the transfer function of Capleton system. Next, after the derivations, we can get the state space equations, which we use to design LQR controller, because LQR controller uses state space equation. And this is the block diagram of the LQR controller in MATLAB. And the state variable form is x equal to ax plus bu. The main objective in LQR controller is to choose the best value of gain k. It can minimize the performance index or cost functions j. The Q is a positive semi-definite matrix, while R is a positive definite matrix. The weighting matrix Q is Q11, 0, 0, Q22, where R is constant and the value of R is chosen is 0.001, and the value of matrix Q is chosen is 9.6 and 42. The value of Q is chosen using try and error between number of 0 to 100. And after that we use the MATLAB coding. We run MATLAB coding in MATLAB to obtain the value of k. Next chapter is the result of the project. First one is the simulation result of trial and error method of tuning PID controller. From the graph, we know that the overshoot is 6.989% and the rise time is 23.554 seconds. Next is the simulation result of automatic tuning PID controller. We can get the overshoot 2.577% and the rest time is 9.218 seconds. And both of automatic tuning PID controller using step value is 60 to reach steady state. Next chapter is about the simulation result of LQR controller. The overshoot is 0.505% and the rest time is 9.297 seconds. And the conclusion is PID controller and LQR both are suitable to be used to maintain and control level of liquid of couple tank system. Both of these controllers can almost achieve zero steady state error. By comparing the best tuning output for PID and LQR controller, we can determine which controller will give a better performance to the system. As the result, LQR controller can provide a better output performance than PID controller with no overshoot at the transient response. And that's all from me. Thank you for watching.